Hi, welcome to the presentation. We're team number 14 and our project is Geothermal Power Plant at Salton Sea. This is the outline of our presentation. We will first be talking about the resource identification and evaluation, followed by the project development and environmental concerns, and followed by the project performance and cost analysis. The resource identification and evaluation. The United States is the global leader in installed geothermal capacity with approximately 3,086 megawatts of installed capacity and is expected to continue the leadership in the next decade. The first US geothermal power plant was built in early 1930s at the geysers in California in the same location as the first large-scale plant which began operation in 1960. It has been found that the significant geothermal resources exist near the Salton Sea, which is approximately 375 megawatts of existing development with an estimated potential of 1600 to 2400 additional megawatts. Amongst the renewable energy sources, geothermal energy is considered as one of the most desirable energy as it can be used as a baseload energy resource and can be controlled to match system loads. The main advantages of geothermal energy are listed below. Domestically accessed and natural. Geothermal plants have very low carbon dioxide emissions, which make them really environmental friendly, unaffected by natural surface conditions such as weather. Then the operating rate of these plants can be as high as 70%, and compared with solar power, which is like 12% and 20% of wind power plants. Geothermal plants can supply reliable base load power. Let us look at the different techniques used for power generation. The basic idea behind harnessing geothermal energy is that the source of heat in geothermal projects are underground geothermal fluids. To tap this energy, wells are drilled deep into the crust of the earth in order to allow us to tap into the steam and hot water reservoirs. The three main methods of producing electricity from geothermal energy are as follows. The first technology is called the dry steam plant. In dry steam plant, dry steam is produced from the reservoir and piped from wells to the plant to directly turn the turbines. This technology composes less than 40% of electrical generation in the US geothermal market, possible when the reservoir produces only high temperature steam, example the geysers in California. The flash steam plants is the second kind of technology. Here, the geothermal fluids lose pressure as they rise to the surface and flash, that is, they boil, in order to create steam that turns the turbines. This composes about 45% of the electrical energy generation in the US geothermal market. This technology is better suitable for higher temperature reservoirs with a mix of hot water and steam in order to allow for an easier transition from water to steam. Example is the Dixie Valley in Nevada. The third type of technology is the binary cycle power plants. This technology passes geothermal fluids through a heat exchanger to boil organic fluids that vaporize at a lower temperature than water. This vapor turns turbines, then condenses, repressurizes, and returns to the heat exchanger in order to be used again in a closed loop. This composes about 15% of electrical generation in the US geothermal market, but is most common on on units installed basis. The technology used in our project is called the triple flash steam plants. In this technology, basically, while the three technologies discussed earlier are typically used autonomously, they can also be used in conjunction with one another. In order to achieve higher efficiency, in our project, we have chosen the triple flash steam plants. As discussed in the flash type plants, the liquid phase geofluid is flash evaporated to a lower pressure in order to generate vapor for power generation. Flash type is often applied when the geofluid exceeds 150 degrees centigrade. It is observed that the system and its operation and maintenance complexity increases with the number of flash stages. A triple expansion plant uses superficial geofluid. It is a variant of the flash plant with the additional topping super pressure turbine, where the SPT is designed in order to handle pressures exceeding the critical pressure of water, which is 22.06 megapascals. The supercritical geofluid expands in the SPT to vapor liquid mixture phase, which is the state 2. Then the mixture is separated isobarically in the CS as shown in the diagram to vapor 3 and liquid 4. Vapor 3 is then fed to the HPT, and the liquid 4 from the CS is flashed again in the FL as shown in the diagram. The mixture of the exhaust from 7 and from HPT and the vapor 5 from the FL are then fed to the LPT. The condensed geofluid 9 is pressurized in the same pressure as liquid 6 from the FL and then re-injected into the underground reservoir. This way, power is generated in all three turbines. The following slide represents the geothermal project requirements. The annual energy consumption per person in LA is calculated to be around 6,400 kilowatt hours, and hence the annual power consumption per person in LA turns out to be around 730 watts. The total number of customers in LA is around 100,000. In order to meet the power demand for so many customers, we require the electric power to be around 220 megawatts. In order to meet the power requirement for 100,000 customers, we have chosen Salton Sea as the most desirable site for building a geothermal power plant. The figure shows the geological structures in the Salton Trough Zone. The south end of the Salton Sea covers one of the largest geothermal anomalies in the United States. The area can be divided into deep and shallow resources. The geothermal resource area is separated into two temperature gradient regions, the greater than 10 degree Fahrenheit and 8 to 10 degree Fahrenheit region respectively. The first table here shows the current land acreage by temperature gradient. The second table shows the corresponding generation potential in megawatt, which sums up to around 2900 megawatt theoretically. Our requirement in this project is 220 megawatt, which can be easily achieved using the selected area as shown in the map. On analysis, we have chosen the area which is located at 33.32 degree north and 115.84 degree west. Now, Monica will talk about the project development and the environmental concerns regarding our project.
Let's take a look at the environmental concerns. Even though renewable resources are beneficial to the environment, careful planning is needed, as without them, they may cause more harm than the conventional sources of energy. Geothermal energy technologies generally present much lower overall environmental impact than other conventional fossil fuels and nuclear power plants. There are, however, certain impacts that must be considered and managed if geothermal energy is to be developed as a larger part of a more environmentally sound, sustainable energy portfolio for the future. The common environmental criteria that needs to be considered before moving forward with a commercial geothermal project are geologic formations that are not prone to large seismic events, or devastating landslides, or excessive subsidence, compatible land use, drinking water and aquatic life protection, air quality standards, noise standards, GHG emissions, which are greenhouse gases, solid waste disposal standards, reuse of spent fluid and waste heat. Now, coming to the main environmental concerns, let's look at land use and subsidence. Geothermal fields span vast area. The area used by drilling can be minimized by using directional drilling techniques through which multiple wells can be drilled from a single pad, thus decreasing the total wellhead area. And the other solution is pipelines. These can be mounted on stanchions so that area could be used for other purposes. Also, a planned reservoir management can be adopted to reduce the risk of land subsidence. Coming to the emissions part, the plant produces a lot of fluid. This discharge of geothermal fluid leads to various problems because it contains chemicals that cause severe threat to living organisms. Mitigation measures like reinjection of geothermal fluid can be used for establishing controlled and balanced harnessing. As you can see in the above picture, it is very easy to work around with the pipelines. The plant produces a lot of solid waste as well. Proper disposal activities must be taken care, and this toxic sludge should be transported safely to designated sites and properly disposed of. This area should be periodically monitored for any harmful effects. Let's talk about the gas pollution. The vents steam from the cooling towers are filled with non-condensable gases such as ammonia, methane, and many other gases. They must be scrubbed and recompressed and then injected back into the subsurface during the reinjection. Also, care must be taken regarding the toxic sludge which is produced during scrubbing, and it must be disposed of at hazardous waste dumping sites. Uh, Now, the water pollution. Water pollution is the most important concern of geothermal plant because liquid streams from well drilling and stimulation contain a lot of poisonous gases that harm local vegetation. And these liquid streams might enter environment through surface runoff. Care should be taken so that the brine doesn't seep into the ground, polluting the aquifers. This is done by holding ponds that are lined properly, making it impermeable, and well casing with multiple strings must be designed. We also re-inject the used water into ground instead of discharging. This prevents the pollutants from entering the surface. Thermal pollution. The rejection from geothermal plants is higher than that of fossil fuel and nuclear plants. So, water used for cooling towers must be brought to appropriate temperature before it's discharged to the appropriate sink. That's the reason why cooling towers are a way larger than those in conventional power plants of the same electric power rating. Regarding the catastrophic events, most of the geothermal sites are present in geologically active parts of the world. Appropriate safety measures must be provided to safely shut off wells or plug them in case of earthquakes. Fast acting blowout preventers are used to eliminate this problem. Also, the risk can be minimized by siting plants away from major fault lines. The socio-economic issues. Although geothermal plants have the least visual impact compared to all other renewable sources, care must be taken in order to restore the area to its original natural appearance. For this, reforestation and plantings must be done. And we should also perform socialization campaigns. This can be achieved with the involvement of local communities. This project can also provides new jobs to the locals. This really helps the affected localites. Now, let's move to project siting and permitting. We need to identify the permitting issues and responsible agencies, and also seek blanket permits from multiple geothermal project developments located near or under Salton Sea. We should also identify and integrate project development with benefits for Salton Sea restoration. A blanket permit approach reduces the development timelines. Geothermal power project permitting varies from that of other thermal power plants. The Energy Commission conducts an environmental analysis of the project as a whole and permits all but the geothermal wells, pads, and pipelines, which are subject to permitting by other agencies. Both the production and injection wells are permitted by Department of Conservation, Division of Oil, Gas, and Geothermal Resources. The well pads and brine pipelines are permitted by Imperial County. Both agencies intend to use Energy Commission's final staff assessment as the CEQA document for their actions. Now, coming to the procurement part, as per the project specifications, we would need 600 acres of land to meet the power requirements for 100,000 people by harnessing geothermal resources in Salton Sea area. Apart from this, additional land would be needed for constructing access roads for the movement of raw materials. Cooling is an integral part of power plants. It is observed that lower the cooling temperature, the higher is the potential plant efficiency. For this, underground pipelines can be laid out connecting to existing IID canals. Also, water required for drilling activities can be supplied via trucks. Due to existing global oil crisis, it would be easier to source the drilling equipments needed for geothermal wells, which would further cut down the initial cost of geothermal power plants. We would need injection and production wells to bring geothermal fluids to surface for utilization and their eventual safe disposal back into the surface. 18 such production wells along with 12 injection wells would be needed, whose dimensions are shown in the slide. High corrosion resistance is required since highly corrosive contaminants such as hydrogen sulfide and chlorine exist in produced steam. Fuji Electric has adopted reactionary blade to reduce stress and erosion and has developed applied metallic materials and coating technology for blades and other components to improve corrosion resistance. In order to meet the project requirements, four such 55 megawatt steam turbines would be needed. We have chosen TVAC generators to produce electricity. A TVAC generator is a totally enclosed water to air cooled generator. They can operate in very dusty and hot conditions because the heat is carried away from them and cooled by pressurized air and water. A 3600 RPM generator with expected power output at 16 kV would be used. Apart from these equipment, step up transformers along with switch gears and generators for power backup would also be needed.
Now I'll be talking about the project construction and the process management. So as you can see in the above diagram, and as we have already previously discussed in the slides, we have decided to go with an onshore land of Salton Sea as our plant location. The power plant consists of Ormat energy converters that each operate independently but share a common ancillary component such as isopentane storage, geothermal brine supply, injection, and substation. We use triple flash steam technology in our power plant design for power generation. The hot water flows under its own pressure from the wells, as you can see these production wells here. As it flows upwards, the pressure decreases and some of the hot water can boil into steam. More steam is produced in the plant by reducing the pressure of the produced fluid in the flash vessel. The steam is then separated from the water and is used to power the turbine generator. So we can see over here that the pipes for the working fluid where the steam might be separated and can be used to rotate the blades of the turbine that essentially help us rotate the shaft, thereby generating electricity. Geothermal fluids from production wells would flow through level 1 and level 2 vaporizers and preheaters of each OEC unit, transferring the heat to isopentane motive fluid through an OEC shell and tube heat exchangers. The cooled geothermal brine, which is shown over here, would then be sent to the geothermal brine injection system without coming in contact with the atmosphere in a closed loop system. So this completes the closed loop system for us. The vaporized isopentane working fluid from level 1 and level 2 vaporizers would turn the level 1 and level 2 turbines, which are believed over here, but for representation here is one turbine, which together turn a common generator that produce electricity that is delivered to a substation where it is finally delivered with the help of transmission lines to the residential customers here. And as we know, the use of the isopentane here is a closed loop system. Water from the condensers is cooled in the cooling tower by evaporating the circulating water, which can be shown in this diagram here. We also have a vapor recovery unit to provide a mechanism to minimize emissions of isopentane from the OEC unit during maintenance, and this would obviously be in the power plant as shown in the diagram. We also have provisions for a control system, an office, a maintenance shop, parking, and other facilities located at a power plant to control, manage, and maintain the project operations, as in the case of any power plant today. Pumps, tanks, valves, control, and flow monitoring, and other necessary equipments for the wells and pipelines would also be required for the project. The transmission lines, which are obviously just shown over here for representations, or the interconnection transmission lines with poles will be needed to transfer electricity to the existing power distribution grid. This will include double circuit 16 kV interconnection transmission line as discussed previously with 66-foot high poles. Look at the performance and cost analysis for this project. To assess the project economics, we decided to use CREST, or the cost of renewable energy spreadsheet tool developed by National Renewable Energy Laboratories. In the above diagram, you can see the CREST model, which is an economic cash flow model designed to allow policymakers, regulators, and renewable energy community to assess project economics, design cost-based incentives, and evaluate the impact of various state and federal support structures. The CREST model also allows users to analyze any renewable energy project using 14 separate input categories, 4 of which are listed here, inclusive of project size and performance, cost level of detail, which is the exploration cost and confirmation drillings, cost-based tariff structures, and operation and maintenance. Let us now talk about the installation cost in per kilowatt as well as the total installation cost for our project. As you can see with the different plant attributes that have been mentioned over here, such as the generator gross nameplate capacity of 220 megawatt and the annual energy production being almost 1.8 gigawatt hour, and assuming an annual plant production rate of 0.1% and a project useful life cycle of 30 years, and we have based on our requirements for achieving a 220 megawatt capacity and all of the procurement for the different equipments, the installation cost per kilowatt comes to around $6,017 per kilowatt. Let us look at how this cost breaks down across different categories for the different developmental stages in the project, such as resource identification, that is associated to 1.2% of the cost, resource evaluation including permitting and steam gathering, that is associated to 20% of the cost, test well drilling, that is explanatory drilling, that is associated to 15% of the cost, production well drilling, that is associated to the 22.6% of the cost, plant construction including transmission lines installation is the highest contributing factor here with almost 41% of the cost. So these being the inputs for the model, we have two outputs for the CREST model, such as the net cost of energy for year 1 and net nominal levelized cost of energy. The primary output is the model project's cost of energy, which is the year 1 price is necessary for a project to meet all expenses and debt service obligations as well as equity investors' minimum rate of return. The secondary output, or the net levelized cost of energy, is a single fixed non-escalating value over an incentive payments duration. Let us now look at the cash flow analysis for the project. The cumulative cash flow analysis, which is on the y-axis and the time period being on the x-axis, begins with a high negative cumulative cash flow of 842 million at time period 0. This is associated with the high equity investment that is required in the beginning to jumpstart the project. And around fifth year, we achieve a positive cumulative cash flow of almost 25 million, and this continues to grow almost linearly and saturating at $1.2 billion at the 30th year mark. Let us now look at the resource potential graph and the production profile. The power plant production capacity depreciates annually by 0.1%, and the resource potential with only initial drilling capabilities depreciates by almost 60%, as you can see in this gray colored graph here. The CREST geothermal model allows up to 2 major well replacements on the life of the project at the 10th year mark and at the 20th year mark. And with these upgrades, we were able to curtail the depreciation rate to almost less than 50%. Continuing with the project performance, let's now look at the project schedule. The slide shows over here the project schedule for the geothermal facility construction from design to operation. The first step is to visit the site and do the analysis. It generally takes about 1 to 5 weeks depending on the size of the site. During this phase, various factors like resource availability, site access, etc. has to be analyzed carefully. The next step, which is the permitting, this takes about 3 months. During this phase, we have to get various permits like environmental approvals. The third phase is engineering. This is an actual construction of the facility. It takes about 2 to 6 months depending on the facility size and the complexity of the technology used. The fourth step is procurement. This takes about a month. In this phase, we procure the turbines, control system, instrumentation from various vendors. The next phase is the installation. During this phase, all items procured in the previous phase are installed. And this takes about 1 to 2 months depending on the size of the project. The last phase, which is known as testing, takes about 2 to 3 weeks depending on the complexity and the size of the facility. And this has to be done before letting the plant for a regular operation in order to ensure safety. Here you can see the project timeline. And we should be able to complete all of our work and start operation by June 2017. Here we have listed the different financing options for the project. Federal incentive schemes such as investment tax credit proved to be a saving grace for clean energy projects. For our cash flow analysis, we have considered a more cautious value of 20%, though the current rules and regulations allow up to 30% of the value of the facility to be the ITC credit. The government and the private funding proves to be another option, and various governmental bodies such as Department of Energy and Internal Revenue Services sanction loans for clean energy projects to assist developers, energy developers like us, in completing these projects. These include the loan guarantee programs at the DOE, the clean renewable energy bonds, and the qualified energy conservation bonds offered by the IRS. For the above cash flow analysis, we have assumed 50% of the cost coverage to come from equity investors or private investors. There are other options as well, for example, direct public finance schemes and bank loans. For our cash flow analysis, we have assumed a debt service reserve, which considers a loan from a bank that finances 50% of the project cost with a 15-year payoff term and a 7% interest. With the operation and maintenance issues, there are two kinds of maintenances which we can follow to keep our plant in best shape. Preventive maintenance is carried out at a predetermined intervals or corresponding to prescribed criteria and intended to reduce the possibility of failure or performance degradation of the plant. Corrective maintenance is carried out after a failure has occurred and is intended to restore an item to a state in which it can perform its required functions. There are several operation and maintenance issues which we have to handle periodically. The most important one being the scaling issue. Since the underground water contains various minerals like calcium sulfates, it can easily corrode the turbines and metal pipes, reducing efficiency of the system drastically or even sometimes completely damaging the facility. We have to take care of this by regularly cleaning the pipes and using some sort of a corrosion avoidance technique. Noise. This is primarily caused by moving turbines, transformers, and cooling towers. This can be reduced by the addition of mufflers or other soundproofing equipments. Air quality. During the regular maintenance, since there is a lot of vehicular traffic and people involved, it can lead to air quality reductions. Since these plants are previously in inhabited place, the sudden increase in vehicle and people can be disturbing for the environment. Water resources. Water are required for replenishment of the geothermal reservoir through reinjection and also serve as a coolant in the turbines. Hazardous materials and waste management. Proper care has to be taken to handle these hazardous materials generated during routine operations and maintenance activities. Visual appeal. Releases of steam fumes from the geothermal power plant will adversely affect the visual appeal due to the presence of facility structures and increased vehicular traffic on the site. Other O&M issues include operator training, technologies like SCADA, and operation manual. Here's a list of our references. This is the team. Thank you.